Okay, Assalamu alaikum wa rahmatullahi wa barakatuh. Hello again, my dear students. And we are on week 2 of physics. And today we have quite a bit to get through. So, without further ado, let's get right into it. Week 2, displacement and velocity. We're going to be talking about the following. We're going to be differentiating between distance and displacement, speed and velocity. We're going to be talking about vectors and scalars. And we're going to analyze motion through graphical representations. We might not be doing that today actually, but we'll be doing that soon, perhaps in the next video, that last part. Let's have a look. So, displacement and velocity. So let's first of all talk about what is the difference between displacement and distance. So we've got two different things here. If we look at this biker over here, this bicyclist, so what's he doing, the cyclist, is he's going from one point over here and he's going to this point over here. This change in position is known as displacement. So as the name suggests, placement is where things are. Displacement is when you move things from where they are. So displacement is a change in position. It's the shortest distance between two lines, between 2 points. Sorry, so it's a straight line. It's the shortest distance between 2 points. So what is the difference between displacement and distance? If we look at an example like the one I'm going to draw right now. Let's say, for example, you start at point A and you walk around and you go all the way to point B. Okay, and here's point B. Okay, now the distance that you traveled as you go from point A to point B might be about, let's say, 17 kilometers. So the whole distance there, every single step you took, that whole distance might have been about 17 kilometers. However, if I use a different color, I'm going to use blue, the displacement is going to be the shortest distance between those 2 points, which is a straight line. And that's going to be shorter in this case. So it might just be about 8 kilometers. Okay. So that's just a very, very quick summary of the difference between displacement and distance. So distance is the total journey, length of the journey, whereas displacement is the shortest distance between two dots, or a straight line. Okay, so the shortest distance between 2 points, which is obviously going to be a straight line. So let's talk about another example, and hopefully it'll make a bit more sense. Okay, and as we solve some problems as well, it'll make more sense as well. Let's say here's point A, and let's say point B is over here, and let's say a person walks from point A to point B and back again. What is their displacement? Well, their displacement is they haven't changed. Their displacement is basically the difference from where they started to where they ended. So displacement is defined. Okay, I can do better than that. Displacement is defined as change in position. X refers to position here. So another way of saying it, it's the final position, which is xf minus x initial. So that just means, that's just a fancy word of saying final position minus initial position, or the starting position. That's displacement. Final minus start. Okay, the end minus the beginning. So in this case, the previous example that we just stated, if a person starts at A and they walk all the way to B and then they come back again, their final position is still A. So A minus A means their displacement is going to be 0. Okay? Whereas their distance is not going to be 0. The distance covered might be 5 kilometers one way and 5 kilometers the other way. The other thing that we need to talk about is that displacement has a direction. Displacement points to a certain direction, whereas it's a vector quantity, so it has both size and direction, or magnitude and direction, whereas distance doesn't. Distance is mainly just a magnitude or size. So let's say in the example I've just mentioned, the distance covered by the person is going to be 10 kilometers, whereas the displacement is going to be 0. Let's do another example, because the more examples we do, the better you'll understand it. Let's say this person has started at point A, and then they've gone to point B, and then they've gone to point C. Okay? And so now, what is going to be the distance? Assuming this is about 3 kilometers, say, and let's say this is 2 kilometers. What's going to be the total distance? Total distance is going to be the total journey, so that's going to be 5 kilometers. That should be easy. Their displacement, however, their change in position, is going to be a little bit trickier to calculate, because remember, the change in position is going to rely on their final position minus their initial position, and it's the shortest distance between two lines. Both of these definitions are true, so this is going to be their displacement. The line in red, the resultant vector, is going to be the total displacement. This here is going to be the displacement. Okay, why? Because it's the shortest distance between two dots, shortest distance between two places, the shortest distance between 2 points. Okay, and as we do more examples, it'll become a bit more clear. So here's another example. This one says that a person has started over here, and then they ended up over here, and you can see that they've kind of walked in this wiggly line. And so it's asking what is going to be their distance and what is going to be their displacement. So in this case, we don't know what the distance is, because we'd have to measure all of this, and the only way we can measure that is using a rope of some kind. But their displacement is going to be the shortest distance between those 2 points, which is a straight line. So we can work that out using Pythagoras theorem, because we've got the opposite and we've got the hypotenuse. And if you remember from maths, Pythagoras theorem states that for a right angle triangle, I can do a better opposite. For a right angle triangle, we take this side. If we have this side and we have this side over here, we can work out this side over here. So c squared equals a squared, and a can either be this or this, it doesn't matter, plus b squared. Or another way of putting it is that c is equal to the square root of a squared plus b squared. And so I can work out c. C is going to equal the square root of 100 squared plus 50 squared, and therefore c is going to be the square root of 12,500. 100 squared plus 50 squared, that's 12,500. The square root of the answer is going to be approximately 111 meters. Why is it 111 meters? It's the shortest distance. So this is going to be 111 meters. That is the displacement. Okay, so we've just worked out the displacement. Okay, let's look at, just a quick reminder, displacement is the shortest distance, a straight line, between 2 points. And it's the final position minus the initial position. And if we want to be accurate, we have to say the direction it's heading in. So we can't simply say it's 111. We have to say 111 meters. 111 meters what? Northeast. Okay, because it's pointing to the northeast. If we know the exact angle, that's even better. So the exact angle is going to be 50 over 100, which is 0.5. So shift tan 0.5, and that's going to be 26 degrees above the x-axis. So that's allowed. You can say that, or you can say northeast. Okay, either way, the displacement has a position. It has a size and it has a position. It has a size and it has direction. Okay? So which way it's pointing to is important as well. So what is the difference between a vector and a scalar quantity? In short, scalar quantities have a magnitude, whereas vector quantities have both magnitude. Magnitude is just a fancy word which means size or length, and direction. Okay, so examples of scalars are things like distance, speed. Examples of vectors are things like displacement and velocity. And we'll see how those two things are related. Okay, so here's an example of the Pythagoras theorem that we just used. There's a bit of a lens flare on the camera over here. I don't know how to fix that. Hopefully it's not too distracting. So anyway, Pythagoras theorem can be used to work out the hypotenuse of a triangle, as you may already know. And that helps quite a bit when we are trying to work out the hypotenuse. If we have a triangle, or if we have the situation like the one we faced before, where a person walks to the right and then goes straight ahead, then that's one way we can do it. Here's an example that we can solve. I'm going to give you some time to solve it. Pause the video, please. Try to solve it yourself, and then play the video and see if you've got it right. Changing classes, you walk 20 meters down the hall. So let's say you walk 20 meters down the hall. And then what do? You turn left, and then you walk 10 meters down another hall. Okay. Define the coordinate system and draw the displacement vector in the space that follows. We've gone 20 meters north and 10 meters down another hall. Well, it doesn't say 10 meters left, but assuming it is, we have another triangle. So obviously the displacement is going to be the shortest distance between the beginning and the end. So it's going to be this here. That's going to be the displacement. Okay? And you can refer to displacement as absolute D. You can refer to it as delta X. There's many ways of expressing it. It doesn't matter as long as you know that displacement is simply the final position minus the initial position, or in this case it's going to be the hypotenuse. So it's going to be 10 squared, which is 100, plus 20 squared, which is 400. So the square root of 500, which is somewhere around 22 maybe. Square root of 500, which is 22.4. Okay, so that's what we're looking at for this answer here, 22.4 meters. Okay, let's keep going. Okay, so here's a good example we can use. What is the displacement for a trip from the physics classroom to the music classroom and then to the math classroom? So the first thing you need to do when you're reading a question like this is you need to figure out where's your starting point. So your starting point seems to be the physics classroom. So that's the starting point, A. And then we go into the music classroom, which is B. And then we end up in the math classroom, which is C. So it's asking for the displacement. Remember, displacement is by definition the final position minus the initial position. So I'm not interested in the music classroom because that's just in between. So I'm going to look at the final position. So change in X is going to be X final minus X initial. So that's going to be, what's the X final? It's going to be 8 meters minus the X initial, which is 5 meters. And of course the answer is 3 meters. Are we done? Not quite. We need to know the position. So 3 meters, and I would say 3 meters forward or 3 meters to the right. It doesn't matter as long as you indicate clearly that it has a direction and the direction is correct. Okay? So as long as you say it's 3 meters forward or 3 meters or positive 3 meters, you can say positive 3 meters if you want to, or you can say 3 meters to the right, or you can say 3 meters to the right of the physics classroom. I don't care what you say, as long as it's clear that you are indicating a direction. So 3 meters to the right of the physics classroom, 3 meters forward, or plus 3 meters, that's all fine. Next question. What is the displacement for a trip from the math classroom in figure 2.4 to the music classroom and then to the library? What is the distance for this trip? So now it's a two-part, yeah? There's 2A and 2B. 2A and 2B. And I'm going to use green to answer. So the first part is asking for the displacement. Now, once again, we need to label the start and the end. So we've got from the math classroom, so that's point A, to the music classroom, which is point B, and then to the library, which is point C. Okay, so if we're looking for displacement, we're only looking at beginning and end. So the beginning is A, so here we go. Change in x, which is displacement, is equal to x final minus x initial, which is going to equal 0 minus 8. Now why 0? Because that's the final. 0 is the final. So 0 minus 8, and therefore the answer is going to be negative 8 meters. And the negative here indicates that we've gone backwards. So that's fine. You don't have to say 8 meters to the left. You can just say negative 8 meters, which indicates that we've gone backwards. Okay. What about the next one? The next one's asking for the distance. Now, distance is the total length of the journey. It's different to displacement. Displacement is final minus initial. Distance is the total length of the journey. So in this case, it's going to be, we're going to go from where? We started at A, went to B, and then C. So A to B, this length here is 6 meters. And then C to B is 14 meters, right? So this whole total distance here, that's 14 meters. So we've got 14 plus 6. Distance is going to be 14 meters plus 6 meters, which simply equals 20 meters. And we don't need a direction for the distance. In fact, distance is a scalar, and scalar quantities do not have a direction. So you just say the size, it's 20 meters, that's all you need to say. Okay? Let's keep going. Okay, here we have another example, and this one is one where we have to use that theorem that we're so fond of, that Pythagoras theorem. Okay? Let's see if we can figure this out. So we've got Banford is about 1,000 meters north and 1.7 kilometers east of Hartmouth, right? So here's Banford and here's Hartmouth. And what do we need here? Use Pythagoras' theorem to calculate the direct distance between Banford and Hartmouth. Give your answer in kilometers to one decimal place. Kilometers. In New Zealand we say kilometers. In American we say kilometers. So you'll notice that I changed my accent slightly so that my students understand me better. But maybe one day I'll do a video all in New Zealand accent and see if you can understand me. Anyway, so Banford is 1,000 meters north, and then we've got Hartmouth, which is 1.7 kilometers to the east. So the first thing, very good practice, is just to label the diagram. That just makes so much sense to me. So 1,000 meters and 1.7 kilometers. All right. Now the next thing I need to make sure that I understand fully is that they want the answer in kilometers or kilometers, which means I want to change this 1,000 meters and I want to make it 1 kilometer. Why 1 kilometer? Because remember, 1,000 meters equals 1 kilometer. Okay? So now that I have my units sorted, I can work out the displacement, which I'm going to use red for. So that's the displacement, or I can use delta x, which I really like using because it makes sense. It's like the definition. Delta x, the final x minus the initial x, the final position minus the initial position. So can I work it out? Of course I can. All I need to do is realize that delta x is going to equal the square root don't forget the square root of 1 squared plus 1.7 squared. And that's going to give me square root of 1 squared plus 1.7 squared oh, calculators are a pain sometimes. And it's telling me it doesn't want to work. Okay, so 1.7 squared equals 2.9. So the square root of 3.9, and that equals 1.97 kilometers. Now, if it says to 1 decimal place, it wants me to go over here, 1 decimal place. So there's a bit of a trick here, and the trick is such that it has to be to 1 decimal place. Now, I can't go 1.9 because the 7 rounds up, so it has to be a 2. So what do I have to do? I go 2.0 kilometers. That's the answer. Okay, let's keep going. Practice C. A train on a straight track goes in the positive direction for 5.9 kilometers. So here's the train. And I'm going to draw a couple of carriages. And it goes in the positive direction. So what I'm going to do is I'm going to draw it the other way, because I think students are used to like basically the positive x direction in maths and stuff. So this might make it a little bit easier. So it's going that way, and it's going that way for 5.9 kilometers. Okay? And then backs up, and then comes back 3.8 kilometers. Is the distance covered by the train greater than, less than, or equal to the displacement? Well, of course, the distance is going to be greater than the displacement because it went forward and then it came back. The displacement is basically the change in position. So if we look at the displacement is going to be 5.9 minus 3.8. The displacement is going to be 2.1 kilometers. 2.1 kilometers forward, or plus 2.1 kilometers. Whereas if we look at the distance, that's the displacement. The distance, on the other hand, is equal to 5.9 plus 3.8. So the distance is going to be 9.7 kilometers. So obviously the distance is much bigger than the displacement. And we've just answered the question. So the displacement is going to be 2.1 kilometers forward. The distance is going to be the total journey, which is going to be 9.7 kilometers. Here is a challenge for you. So practice D. I'd like you to try and give it a go. Please try and give it a go yourself. I didn't realize I was wearing these. I'll just take these off. Okay, so try and do it yourself. It's not that hard. What I find is sometimes the students have a bit of a problem understanding the question. So if you read the question, always read the question twice if you can. Read the question twice and answer once. Try not to doubt yourself too much. Read the question twice, highlight what's important, and then answer once. A jogger runs on the track shown in this figure below, neglecting the curvature of the corners. That means you neglect these curves. What is the distance traveled and the displacement in running from point A to point B? Find the distance and displacement for the complete circuit. So first and foremost, I have to realize that there are two parts to the question. And the first part is asking me about the distance traveled and the displacement and running from point A to point B. So if I look at the displacement is quite easy. It's the shortest distance between point A and point B, and that's going to be a straight line. Here's point A, here's point B. The shortest distance between point A and point B is going to be 100 meters. So the displacement, that's easy. That's going to be 100 meters. Now what about the distance? The distance is going to be slightly trickier, because now we have to look at how the runner is going to get from point A to point B. So first they have to go down. Remember, we're ignoring the curves. So then they're going to go all the way. Of course, I can't draw a straight line when I'm... Here we go. That's as good as it's going to get. And then back up. So if we ignore the curves, then we know that that's 15 down and that's 15 up. How do I know that? It's about halfway down this way. So 15 and 15, and then we have 100. So therefore the distance is going to be 130 meters. 15 meters down, 100 meters forward, and then another 15 meters up. Okay, what about part B? Let's go to part B and find out what they want. Find the distance and the displacement for a complete circuit of the track. So if they start at point A and then they finish up at point A, so they do a complete circuit, they go around one time around the whole track. What's going to be the distance? What's going to be the displacement? Well, the distance is quite easy because let's start with the distance. The distance is going to be 100 this way, 30 meters that way, 100 that way, and 30 meters down. So if you're good at maths, you should figure out that that's about 260 meters. And distance doesn't have a direction, whereas displacement does. And what about the displacement? Displacement, well, we started at point A, and we ended up at point A, so the displacement is 0. And in this case, there's nothing to say about direction or anything like that. It's just 0. Because we started at the same point that we ended up in. We go in a circle, so the displacement is going to be 0. By definition, it's the shortest distance between 2 points. By definition, it's the end minus the beginning. So displacement is 0. Okay? There we go. So let's summarize. What is the difference between distance and displacement? Distance is... Does that even work? Nope. So distance is the total journey, length of the journey, and it is a scalar quantity. It does not have a direction. Displacement, on the other hand, is a vector quantity. It has both magnitude and direction, and it is the shortest distance between 2 points. Whereas the distance is not necessarily the shortest distance the shortest length between 2 points. What is the difference between a vector and a scalar? So we've kind of answered that already. A vector quantity is one that has both size and direction, or magnitude and direction, whereas a scalar quantity is one that only has size. So for example, if I talk about length, I might say that's 1.7 meters. If I talk about my length, I might say that's I'm 1.72 centimeters, 1.72 meters, sorry. I'm not going to say I'm 1.27 meters up or down. So that's a scalar quantity. What if I say, for example, the speed the car is moving is 70 kilometers per hour? That's a scalar quantity, because I'm not saying it's moving forward or backwards or to the side or whatever. But if I change that and say the car is moving at 120 kilometers per hour north, suddenly it's the velocity, and we're talking about a vector quantity. So vectors have magnitude and direction, or size and direction. Scalars only have size. Okay, and unfortunately I can't see a show of hands, so we're going to move right on to the next lesson. Oh, we've got homework here that I'm going to help you with. So once again, please pause the video and try and do it yourself before I do it. Changing classes, you walk 30 meters down a hall, 30 meters, and then you turn left and walk 10 meters. Define a coordinate system. So when we say define a coordinate system, this is what we mean, basically. Just draw it properly. Also draw the displacement components and then determine the vector's magnitude. So this is the displacement component, and it's going to be the hypotenuse, and we're going to give it a fancy delta x. So that's going to be 100, because of course delta x is going to equal the square root of 100 meters plus 900 meters. So it's going to be the square root of 1000, which is approximately 32 or 33. Square root of 1000, and that equals 32 meters. What is the total distance covered? So the total distance covered is 40 meters, because we know they went 30 up and 10 to the left, so that's 40 meters. And the total displacement, we just worked it out, it's about 32 meters. Now I'm going to ask a question at this stage, and I want you to think about it. When is displacement equal to distance? Think about it for a while. When is displacement equal to distance? There are two scenarios where displacement is equal to distance. The first one is if the person is stationary or if the car is stationary. So if the person isn't moving, if they're at 0 and they're not moving, then displacement is equal to distance because they haven't gone anywhere. The other scenario is if they go in a straight line. If a person travels in a straight line, the shortest distance between 2 points. Let's say, for example, they start here and they go over here and they go in a perfectly straight line, which I'm not going to be able to draw. That's as good as it's going to get. Then in that case, let's say, for example, it is 5 kilometers. And so the displacement is going to be equal in magnitude to the distance. So the displacement is also going to be 5 kilometers because it's the final minus the initial. So if the person is going in a straight line, or if they're not moving at all, then distance equals displacement. Otherwise, it is most certain or highly likely that distance is nearly always going to be bigger than displacement or equal, but never smaller. So most of the time, distance is bigger than displacement. Okay. If you want to go take a break, drink some coffee or tea, and then come back and we'll continue the lesson. As for me, I'm just going to continue. Let's go. So vector maths. So when we're talking about displacement, remember I said displacement is a vector quantity. If we go back to that diagram, this is essentially a vector. It has a tail and it has a head. That's what we mean by a vector, right? Vectors have head and tail. So the head is represented by this arrow and the tail is represented by the no arrow. So that is an example of a vector. Okay? I'm going to skip right through this problem. Let's go to the next one. How do you add vectors together? So I don't want you to worry about this too much. Let me just give you an easy way of doing it. Here's a vector, and here's another vector. How do I add them together? The way you add them together is you add the head to the tail. Okay, that's what you do. So I want you to imagine, for example, a fish. And this fish wants to eat this fish. Okay, and what's going to happen is this fish is going to go and bite the tail of this fish. Okay, so I hope that makes things slightly easier to understand. So we put the head to the tail. So what I'm going to do is I'm going to draw very carefully. I'm going to draw this vector over here. So that's the first thing I do. And then what do I do next? Because we're not done. I've just put the head to the tail. That's the first thing I did. And then what I'm going to do is I'm going to draw another vector this time. And that goes from this tail all the way to this head. And I'm going to call that resultant vector. And it's the result of adding those two vectors together. That's what that means, the resultant vector, right? So somebody might be asking right now, so hang on, what if we added the other way? What if we put this tail to that head? So let's say, let's do that. Let's see what happens. So here's the same vector, vector A, and this is vector B. So let's take vector A once again. And this time we're going to add B's tail to A's head. And let's see if it makes a difference. Well, some of you clever cookies would have noticed that it doesn't make much of a difference. And if I go like that, then I'll notice that this R is exactly identical to the R we drew above. So it really doesn't matter which one you put on which end. So as long as you add the head to the tail, you can add the first vector's head to the other vector's tail, or the first vector's tail to the other vector's head. It's going to work either way. Okay, concept check. Let's rank these vectors in order of increasing magnitude. So once again, magnitude just means size. So increasing magnitude just means increasing size. And we're starting with the smaller one because they want us to increase. So that's going to be B first, and then I think we're going to go with C second, and A third, and finally D is the fourth one. Okay? And that is my ranking. Let's keep going. Right. So, very quickly, without going into the whole hoo-ha of the whole thing, when we're adding vectors, there are two ways of adding vectors. So let's go back to the example of A and B. Now I don't really have a grid over here, so I'm just going to make one. And it'll have to do. Okay, now I'm going to draw two vectors here, one in blue, and that's going to be like that, and another one in orange, not orange, red, and that's going to be pointing this way. So what I want to do is I want to add them together, right? Now there's two ways of adding them together. I can actually go and very carefully take the red vector and add it to the blue vector by putting the tail to the head, which is what we did before. That's called the graphical method. Okay, so that's basically just taking one vector and adding it to the other. The other way I can do it is I can actually figure out the x and y components. The what now? The x and y components. You see, vectors have x and y components. C, it has a length, which is y, and it has a width, which is x. And this guy is the same. It has a length, which is y, and it has a width, which we call x. So if we put them over here, it's clear to me that, for example, the blue one is going to have, oh, I want to stay consistent with the colors just to make it easier. So the blue one, of course I would do that. Let me try that again. That's better. So the blue one has a width of 2. So if we just put some labels here, and it has a length of 2, right? So that's 2 and 2. Well, the red one has a length of 1 and a width of 2. So that goes all the way over here. And so that's 1 over here, and that's 2 over here. So the resultant vector that I'm going to draw, that's going to go from one tail all the way to the end. I'm going to use purple. That's what the resultant vector is going to look like. Now the resultant vector has x and y components as well. So if I take this one here to be 2, and this one here to be 1, okay, and this x here to be 2, and this x here to be 2, then I can work out the dimensions of the resultant vector. This is called the analytical method. So you add the x components for both vectors and the y components for both vectors, and then you can find out the dimensions of the resultant vector. Okay, so according to the analytical method, if I take y1 and I add it to y2, that equals 1 plus 2, and that equals 3. So this here should be 3, and it is. And if I take x1 and I add it to x2, x1 plus x2, then hopefully you figured out that should equal 4. Okay, and does it? 1, 2, 3, 4. It sure does. Maths works. So it does work. Great. So there's two ways of adding vectors. You can add the head to the tail, or you can do the components, x and y, and add them together. Okay? Easy peasy, lemon squeezy. Okay, here we have a problem that's a bit of a challenge. And I just included this for those of you that are interested. Okay, so you've got a ski resort, and you've got this person here is taking a rope tow to the top of the bunny slope. Your displacement vector for this trip has a length of 190 meters. So this here is 190 meters, because that's the shortest distance between point A and point B. Displacement is the shortest distance between 2 points. And the angle is 26 degrees Celsius. I bet that's important. That's why they told us that. During the ride to the top, how far have you gone in the horizontal direction and the vertical direction? So here's an example where they want you to work out the components. So this is the y component and this is the x component. How can I work it out? Well, if you remember from maths, we've got something called ka toa. It sounds like Kung Fu Panda. Ka toa. Now, what do we have here? We've got the opposite of the angle, and we've got the adjacent. So we can use tan. if you want to. No, hang on. We don't have both. We've only got the hypotenuse. That's what I meant to say. So we can work out the opposite by saying sine 26 is going to equal opposite, which is y, over the hypotenuse, which is 190. And then we can work out what y is equal to. So sine 26 times 190, and that gives me 83 meters in the vertical direction. That's y, 83 meters. Now what about the horizontal direction? So there's two ways of doing it. Now that I have y, I can go Pythagoras theorem, or I can just go cos, because remember it's SOHCAHTOA, and I want to work out the adjacent, so that's, and I've got the hypotenuse, so I can go cos 26 multiplied by 190, that gives me 170 meters, or 171 meters. Okay, I'm not going to spend too much time on this. I don't expect you to know this right now, but we will visit it again in the future, so I'm not going to spend too much time on it. If you understood it, fantastic. If you didn't understand it, you can go back through it if you want to, or if you feel like it's a bit too challenging, that's fine. We can go back and visit it in a few months anyway. Okay, practice C. Starting from one shore, you row your boat. Row, row, row your boat gently down the stream. So here we go. We've got a river, and we've got a boat. Here we go, and that is our boat. And what are we doing? We are going, it's 30 meters wide. The river is 30 meters wide. It's always nice to draw a quick diagram just to make it easier for us to understand. As you row, the river current moves your boat down the river a distance of 15 meters. So let's assume the river is moving this way. It doesn't really say, but let's assume it's moving this way. So you move forward 30 meters, and then the river moves you this way 15 meters. What's going to be your resultant displacement? Well, lucky for us by now, we're all expert at this. It's going to be this guy here. That is the resultant displacement, which is going to be the square root of 15 squared, which is 225, plus 30 squared, which is 900. So that is the square root of 1125. Unfortunately, I'm not that good at maths. I think it's about 34, but let's look at that. So 225 plus 900, square root of the answer is 34. Yeah, so it's going to be 34 meters. That's two significant figures. Okay, so that's the answer. Let's look at this guy over here. We've got your friend rows a canoe across a river 44 meters wide using the GPS on her phone. She determines that her total displacement is 66 meters. How far down the river did the current move her canoe? Okay, so once again, we've got the same kind of scenario, but slightly different. So what do we have here? The river is 44 meters wide. And her total displacement was 66 meters. How far did the river move down here? So that's what they're looking for. They're looking for this distance here. So the x component, if you want to call it that, or the y component. So we're still using Pythagoras theorem, but we're using it in a slightly different way now. So a squared plus b squared equals c squared. So we know that 66 squared is going to equal 44 squared plus d squared. So I can do this, okay, 66 squared minus 44 squared, and then the square root of all of that equals d. So let's do that, 66 squared minus 44 squared, and the square root of all of that, and that gives me 49 meters. That was a bit challenging. Okay, but it's not too bad, is it? Okay, let's do some vector addition worksheets. Okay, let's see if we can solve these. Now, once again, remember there are two rules to remember here. Two, and only two. Head, okay, that was a terrible star. Terrible asterisk. Head to tail. Remember that, head to tail. Not tail to tail or head to head. Head to tail. And the other one we need to remember is don't change direction. Don't change their angle. Don't change how they're pointing. Don't change the way they look. Okay? So if I want to add this guy to this guy, what am I going to do? I'm going to give you, you know what? I'm not going to give you any time. I'm going to do it. And I've got the answers on the next page. So that's what I'm going to do. But I would highly advise you to pause the video, try and do it yourself, and then check your answers. So even if you've done it, do it again. Okay, just so you're sure. So I'm going to do the first example for you. I'm going to take this and I'm going to add it to that. So what am I going to do? I'm going to take the head and I'm going to put it over here. I'm going to make sure that they're the same angle. That's it. Okay, close enough. And then I'm going to draw the resultant, and I'm going to draw it in blue. And oh boy. Now which way is it pointing? Remember, that's the tail and that's the head. So that's the way it's pointing. And that is the resultant vector. That's the answer. The one in blue is the answer. Okay, so go ahead and try and do the rest of those. They're not too tricky. So what about this one here? Remember, displacement is the shortest distance between 2 points. So this person here might have gone backwards for a bit and then moved forward a bit more. So what's going to happen exactly the same way, I'm going to put the tail to the head, and you'll see that if I do that in this example, then the resultant vector is going to be, oops, I'll do it the same way I did it before. Here we go. So then the resultant vector is going to be in blue again, and the resultant vector is going to be that. That's it. That's the answer. Okay, let's look at the answers now. Here are the answers. So please check your answers, make sure that you got them right. Once again, it doesn't matter how many vectors you have, you see it's always going to be head to tail. And it doesn't matter which one you start with, it's always going to be the same result. Okay? All right. Let's do a quick recap of key concepts. I think that's a good idea. Let's do it. Oh, great. This is classwork, and we got to do a quick recap. Let's answer these questions. So what I want you to do is I want you to answer these questions before I answer them. Pause the video if you have to. In the product A times B, A has 3 significant figures and B has 1 significant figure. How many significant figures does the product have? Well, it's going to be the one with the smallest significant figure, so it's going to be 1. Why is that? Because it's the one that's least accurate, and the answer or the product cannot be more accurate than any of the individual components. So because that's the least accurate, it's going to be the answer. It's always equal to the one with the lowest significant figures. How many significant figures are in the number 1.3240? Well, you might be tempted to say there's 4, but no, the 0 is actually quite significant as well, because it comes after the decimal. So in this case, it's going to be 5. Okay, let's move on. Billy runs 400 meters to Andy's house, turns around and runs 400 meters back home. What is Billy's displacement? Okay, so he's gone 400 meters one way and then straight back home, 400 meters. Now, in order to answer this question, you have to know one fact. What is displacement? Displacement is the change in position. It is the final position minus the initial position. Billy started at home and he ended up at home. His displacement is 0. That's the right answer. Khalid walked from home to school, then from school to the park. What is his total displacement? Here's Khalid. He walked from home to school, so this way, and then from school to the park. what is his total displacement? So it's a bit of a trick question. We actually don't care about any of that. We don't care where he walked. The most important thing here is his final position minus his initial position. So it's going to be that to that, which is the shortest distance, which is going to be 2 kilometers. That's it. The displacement is this, the shortest distance between two lines. From the figure, what is the displacement? This figure here we're talking about. Well, in this case, we need to use Pythagoras theorem because it seems like we're talking about this guy here, the one in red. So it's going to be 15 squared, which is 225. Sorry, it's going to be the square root. Delta x, which is what we're looking for here, is going to be the square root of 15 squared plus 20 squared. 225 plus 400, so the square root of 625. 625, and that equals 25 meters northeast. Don't forget the direction, okay? So what is displacement? 25 meters. It's missing the northeast. It should have a direction. Moving on, a small book is made of 20 pages. The book is 4 centimeters thick. What is the average thickness in centimeters of a page in the book? Rounded to the proper number of significant figures. That is a handful. So 4 centimeters is how many meters? Or do we even need that? We don't. It's 4 divided by 20 because they want the answer in centimeters. So it's 0.2 centimeters. Yep, it's that one. The SI unit for speed is meters per second. Ali runs across the soccer field, moving 10 meters north, then 8 meters west. His displacement would be what? 10 meters north, 8 meters west. What is his displacement? It's going to be the square root of 8 squared plus 10 squared. And that's going to be 164. So it's approximately 13. Let's have a look. So it's going to be that. Because 169 is 13. So it's that. It's 12.8 northwest. Which of the following is not a vector quantity? We know displacement is a vector quantity, velocity is a vector quantity, acceleration is a vector quantity. What about speed? Speed is not a vector quantity. It doesn't have a direction. It's simply just the size. So that is in fact the answer because it's wrong. Express 50 kilometers per hour in units of meters per second. Okay. So the way to do this is, first of all, we change 50 kilometers per hour to 50,000 meters per hour. And then what we can do is we divide it by 50,000 meters per hour is equal to, divided by 60. You don't have to do it this lengthy way. 833 meters per minute. And then we change 833 meters per minute to meters per second, which equals 13.9 meters per second. The other way you can do it is go 50 times 5 over 18 and that will give you the answer immediately. So the other way you can do it is you can do the shortcut. Or obviously that's the closest answer. What is the total displacement of the object represented in this motion graph? Well, we started at 2, that's the first position, and we ended up at D, which is 4 meters. Remember, displacement is equal to change in position, which is going to be, in this case, is going to be D minus A, which is going to be 4 meters minus 2 meters. So it's going to be 2 meters. Now displacement has a direction as well. So I'm just going to say 2 meters up, or 2 meters north, or plus 2 meters. That will do. Next, a person walks 50 meters directly north and then travels 32 meters directly south. What is their displacement? They went 50 meters north and then they came back down 32 meters. So their displacement is going to be this vector here, which I'm going to draw in a different color because I love using colors. This is their vector. So it's going to be 50 minus 32. So it's going to be 18 north. Remember the direction. What is the difference between scalar and vector quantities? Scalar quantities have size. Scalar, they have magnitude only. Vector, magnitude plus direction, or size and direction. Next, here's the final question we have. Sultan rides his bicycle from point A to home, and then before heading to point C. The journey took him 5 minutes. Calculate the speed and velocity of his journey. Fantastic. So in order to calculate the speed, equals distance over time. Distance over time. That's speed for you. And then velocity equals displacement over time. So I need to work out the distance and the displacement. Well, distance is obvious. Distance is equal to 70 meters. And what about displacement? Displacement is equal to this guy here. So it's going to be the square root of 30 squared and 40 squared. So it's going to be 50. Okay. What about the time? I need the time, because remember, both of these formulas require time. Okay. The other way we could do these is by using the formula. That's for velocity, and this is for speed. The triangle, if you like using triangle. So I need time. What is the time? Time is 5 minutes. So can I just simply divide that by 5 minutes? No. Don't do that. Remember, we're talking SI units, so the time is in seconds. So let's do the conversion. Time equals 5 minutes, which equals 5 times 60, or 300 seconds. Now I have everything I need. So distance, so the speed is going to be 70 divided by, so speed is going to be 70 over 300, which is equal to 0.23 meters per second. And the velocity is equal to 50 divided by 300, which is equal to 0.16 meters per second. Don't forget the direction. North, east. And that's the answer. Simple stuff. Thank you very much. We'll stop right there. That is nearly an hour. Sorry, it's slightly longer than I thought it was going to be. All the best for the quiz next week. I will see you in the next one. Adios, ciao, over and out.